Okay, so to be very informal, it's a work in progress with Alexandre Krajenbrink, who will come to the program later in May. And so it's about, the general team is about particle systems in 1D, in a weak noise limit. So in that limit, the typical fluctuation are Gaussian. But one still has some non-trivial large deviations, so one is interested in a large deviation. Sorry? It will come slowly. This is just an introduction. Okay. So we started with, so there's a series of work, most of them with Alexandre. We started with the KPZ equation in a small time limit, in which case it's a small noise situation, weak noise situation. Then we moved to the macroscopic fluctuation theory. And recently we did some weak noise limits for polymers and also for Q-TACEP. So this is this polymer is published. This one, the other one is in preparation. And so these models are integrable, and they have integrability property. And the game is to try to take essentially all integrable stochastic models and to look whether they have a weak noise limit. And in this weak noise limit, one obtains models which have classical integrability, in the sense that they have Lax pair. And I will come back to it. So this is some kind of a general study we're trying to do, and maybe since Alexandre is coming in May, he could talk about present this, because he was the driving force in this work. And in fact, like Alex said, Alexandre is my brain, right? You said that once, right? So today I'm brainless. I couldn't have been so polite. You said it. Okay, so so there are several geometries one can look at. There is a ring, open, or a full space, or let's say the line. Okay, so it's one dimension, a full line. So I'm not going to really talk about this. I just give on a real line. Okay, so let me keep on introduction. So we started with KPZ equation, and then you write it in the form. So let me introduce the partition function, so exponential of the height. So I will write it in the form of stochastic equations. And I'm going to look at some, there is some initial condition at time 0, and I will look at some observation time capital T. So I will look at the distribution of the height, for instance, at capital T. And what happens is that you can rescale time. So you can say that time is T tilde, X, square root T, X tilde. And if you write this equation in the tilde variable, you find that there is here a factor e to the 1/4, which comes in front of the noise. So it means that if you are at short time, you are in a weak noise situation. Okay, and if you have a weak noise situation, you know that the fluctuation of H are typically Gaussian and scale at e to the 1/4. This is the Wilkinson scaling. But there is interesting large deviation function, so one can actually see that the distribution of H can take for H over the 1, so there are large deviation over the 1, and the distribution takes this form. So T again is small. And there's a rate function phi of H, And there are presently two directions to compute this rate function, phi. The first one, yes?
So before you do the short time limits, like for KPZ, you need renormalization.
Oh.
No.
Okay.
So
Please.
what happens to this renormalization?
In the weak noise limit?
Because that could be interesting to see what happened to the regularity structure and so on.
In short time?
In the winter.
Well, okay. I mean, but these works usually are looking at the ultraviolet structure, right? So precisely short time, although I'm not sure. I don't know the answer to this, but okay.
So it's completely washed. You don't see any need of renormalization when
you're right. Okay, so when we do this saddle point and so on, you're right that there is no obvious trace of a need for regularization. That's a good point.
Bizarre because the regularization the stochastic equation is well posed, so it's a short time construction. And then you push it to abstract.
Okay, but
the
somehow it could be
of the equation is first a short time.
Yeah. Well, okay, it's a good point, and deserves some discussion, but okay. Certainly, what is true is that if you do the saddle point, which I'm not going to do in detail, I'm actually coming to this. So let me just say it actually when I will talk about it. So there are two ways to compute this function. First of all, there are some initial conditions for KPZ equation where one has a Freudon determinant formula, and one can then take the weak noise limit of this formula. And the other approach is that at weak noise, one can write saddle point equation. Using dynamical field theory. I will show a bit later, maybe a bit more about that. But when you do that, you get a system which is actually very similar to a nonlinear Schrödinger. And without any need for regularization. And this is actually integrable. And one can, using inverse scattering, compute also the rate function, and this is what we did in 21, and there was a paper by Tsai not very far after that. And the main initial condition, which are droplet, Brownian, and flat, so this rate function was computed by these two methods in both, in these three initial conditions. Where this calculation can actually be performed to the end. Okay, so let me move now to the second example, which is the SEP. So the SEP, if n number of sites and time go to infinity, is actually in a weak noise regime. And it is described, it can be described by macroscopic fluctuation theory. Of course, I will later on be a bit more specific, but and by saddle point equation, which have been studied a lot, and in particular, one of the quantity which people are interested in is the time integrated current. Though I'm going to call it capital G, which is the number of particles of the flux across x equals 0 up to time t. Well, we call it capital T. And using the saddle point equation, for instance, it was shown that the distribution of this current takes large deviation form, which is of this form, where now the large parameter is time. So it's the inverse of this, if you want. And this function phi was computed, for instance, by Better-Ansatz method by Derrida and Gershenfeld. And more recently, there was some, the other type of method was developed, and it was noticed that these saddle point equations actually are related to derivative nonlinear Schrödinger, which is also integrable, and which was solved by inverse, well, some initial condition was solved by inverse scattering. And these are works, so this is B. These are work by Grabsch and collaborator, and also by Malik, Morio, and Sasamoto. And at the same time, approximately the same time, we looked at, I don't know if you can see if I write here, yes? We look at the MFT for the KMP model. Which we found also can be mapped onto the NLS and is also integrable. And this is work of Smith, Merson, and Bettelheim, 21, and our work, 22. Okay. And after that, the last thing is this, as I mentioned, the polymer model. So we looked at the O'Connell polymer. And so in that case, weak noise is like high temperature limit. And we also look at log gamma polymer. And in a weak noise, high temperature limit, they produce some kind of new semi-discrete integrable system, or discrete, semi-discrete for O'Connell and discrete for log gamma. When I say new, actually it turns out that for the O'Connell polymer, it's actually related to a system which was studied before, which is called the discrete self-trapping dimer, which was studied by Sklianin in 1990. But for the log gamma, I think it's new. Huh?
Semi-discrete.
Time is continuous and space is discrete. And this one, everything is discrete. Okay, so
system.
Sorry?
It's not a classical integrable system.
No, they're all classical. In the weak noise limit, they are classical.
Classical equation.
Huh?
Classical equation.
Yeah, classical equation. This is the full point, the main point of this, right? You get always classical. Some classical limit in some sense. Okay, so I will move to now the WhatsApp. So there are some questions on this, or? Okay, so let me. So the question we addressed recently is macroscopic fluctuation theory plus driving, asymmetry, because actually it was lacking exact solution, I mean, to my knowledge at least. And we started by the ASEP. So let me start with the ASEP, sorry. Okay, so as everybody knows, you have these rates, I'm going to call them R and L. I plus 1 and tau goes to tau plus 1. The time is tau, and when tau goes to infinity, under KPZ 1, 2, 3 scaling, this model goes to a KPZ fixed point. So this will be KPZ equation with very strong noise. So this is not what we are interested in, but one can look at weaker asymmetry. So for instance, one can look at L over R, which is exponential minus racine of square root of epsilon, sorry, when you scale space and time. So I will scale space with epsilon. So X will be the continuous space, and T will be the continuum time. Okay, and if you do that, so this is one, if you prefer, it's like one over square root n, where n is the number of sites. Okay, you can think of it like this. Then the height field of the ASEP goes to proper scaling to the height field described by KPZ equation, and this is famous work of Bertini and Giacomini, 97. Okay, so this is also going to KPZ equation, but it's also not what we want because we want actually weak noise KPZ, so something similar to weak noise KPZ. So the rescaling will be the one of the WASEP. So the rescaling of the WASEP, which is even weaker, which is exponential of 2 nu epsilon. And this will lead to a macroscopic fluctuation theory plus driving. Okay. So it's a scaling, which is, if you want, like 1 minus 1 over n. Okay. So let me write down this MFT. So this is, okay, this is the regular, sorry?
Epsilon plus square root of 2 epsilon.
So nu epsilon. It's nu is a, sorry, nu is a parameter which is important.
With proportionality.
Thank you. Yeah, it's a parameter which will play an important role later. Okay, so it is known, and I don't know actually where this was actually proved, but okay, the coarse grain density field satisfies this stochastic equation. Okay, so there is a diffusion term, there is a driving term, and then there is the noise term. Okay, and so this is certainly in the work of Derrida and Bodino 04, but I don't know if this is known before or if it has been proved, not proved. I don't know exactly what the status, and if any of you can tell me, because we're writing papers, so it'd be nice to have a good reference. I mean, the only paper I can trace is this one, but maybe there are others.
And sigma is the same.
So yeah, sigma is the same, yes. And nu is this parameter. Mm-hmm. Okay, and sigma rho for the WASEP is 2 rho, 1 minus rho, and D is 1. Okay, so you can choose units, but okay. With the thing I did is it's like this. Okay, sorry. Well, D is actually L plus R over 2, which is I will choose it to be 1. Okay, so for nu equals 0, one recover the SEP, macroscopic fluctuation theory. One knows that the stationary measure of ASEP is Bernoulli rho. So the stationary measure of the ASEP is Bernoulli rho, where rho between 0 and 1. So one initial condition which one likes is to take the initial density to be ρ1 and ρ2. On the left and right of 0, so I'll call it 0 bar of x. And then if you do with, let's say, Bernoulli, with this parameter on each side, and if you do the WASEP limit, okay, so this is also discussed a lot by Derrida and Bodino. You get a distribution, initial distribution for the profile of density, which is exponential minus 1 over epsilon. So there's 1 over epsilon here. Epsilon will, of course, later go to 0. I forgot to say it, but epsilon is going to be small everywhere. And then there is some formula for the free energy, which has this form for the WASEP. Okay, so that would be the initial condition for the WASEP. Now, ρ1 equal ρ2 corresponds to stationary. Initial condition. ρ1 equal 1, ρ2 equal 0 correspond to step, which is a fully deterministic initial condition. Okay, so this is what we're going to study. And let me now tell you what our main result, one of our main results is. So there will be a formula, which is a bit big formula. I mean, not as big as the one in Alexei's paper, but still bulky.
What is the Z in the
Sorry?
Z in the exponent, the integral?
Easy.
Yeah, sorry, I'm sorry. There is an integral. Yeah, it's just a fancy way to write some logarithm. It's also log of rho 1 minus rho. Rho over 1 minus rho and something.
So the fact that the stationary measure the local.
Yes, it's because
for
the ASEP is Bernoulli, so it's local. So in a limit,
even if you have asymmetry,
yeah, even for the asymmetry.
there is no long range correlation.
Well, it depends. This is on infinite line. I guess on the open, you can have more complicated. Yeah. Okay, so the formula is the following. So first of all, we define rho. We define a height field, so some usual way. And I will also write it like derivative of capital G, which would be a...
That's so the limit epsilon goes to 0.
Yeah, everything I will going to say is going to be in that limit, sure.
Yeah, equivalence of the.
Yeah. Yeah. Okay, yeah. I don't have the calligraphic gifts that you have. Okay. Okay, so I define this integrated current function like this, and so it has to be also defined at x equals 0, and it's defined by the number of particles which have crossed the origin up to time t. So it's equal to this as a function of the density is equal to this. Okay. And now this is the object g of xt, which I want to, I'm going to call it g of xt. And I want to look at its distribution of probability. So I will sometimes, not always, set t to 1. So t is the time in a continuous system. So it means that I erase the rescaling, but it means that in the original SEP, it means that it corresponds to an observation time in the original discrete model, which is the original SEP, sorry, 1 over epsilon square. So 1 over epsilon is like square root of t and correspond to a large time, observation time, but in a rescale system, it will be t equal 1. But I can also keep t in a rescale system and as a free parameter, which is of order 1. Okay, so the formula is the following. On the left-hand side, there is some observable. Okay, so the observable is the expectation value of something, and the something takes this form. And it takes a form which is not too simple compared to other cases of weak noise theory. And this is an average over the noise and initial conditions. Okay, so U is the Laplace parameter. So it's like a Laplace transform. G is the random variable that you are interested in. And okay, so this is the observable, and this is a polylog 2. A D-log polylog 2, and then on the right-hand side, you have that this is take this form, and there is an explicit formula for the function psi of u, which I'm going to write here. Maybe I will. Okay, so it's a contour integral, but it's actually along the imaginary axis. So there is something here. And then, as often in this weak noise theory, there is again, L2 function. Okay, sorry, I'm writing it explicitly because it has some property which I want to emphasize later on. Okay. So the Laplace parameter is here. You have this density ρ1, ρ2, you have nu, and delta has to be between ρ1 and ρ2. So ρ2 is supposed to be smaller than ρ1. And this formula, for now, we know it only in that case, and nu positive. Now, where this, okay, so here, this is for the step, okay, sorry. So this was for the step initial condition. It's not finished, the formula is not finished. Sorry?
E2, I forget.
Forget the definition of LE2?
Yeah.
Take derivative of LE2, you get log. Okay, so it's not finished. So this is the solution. This is observable in the case of the step initial condition. But if you actually looking at ρ1 and ρ2 arbitrary, there is an additional twist, which is that there is a random variable which gets in there. So there's some variable omega. And you have to add an expectation value over this omega. Okay. So this omega has some distribution of probability, which I can write by for completeness, I would say, but maybe, okay, maybe I will not write it in detail. It contains also some L2 with some function of omega. It contains also some L2 function. I'm not going to write it. Well, it's not very complicated, but it's a bit bulky. So the point is that this random variable has an optimal value somewhere, where alpha is ρ2, ρ1, 1 minus ρ2. Okay, so it's a random function, it has a minimum, a single minimum somewhere. Okay, so first of all, where is this formula coming from? It's coming from the limit of a formula by Amol in his paper, relatively recent paper, and also a paper with Alexei and 19, which contain Q deform Laplace transform. So if I have time at the end, I will show how you do the limit on this formula, but I'm not sure I will have time. So it will depend how long the talk you want the talk to last. But okay, so anyway, so there in this formula, there are Q it's a similar kind of formula, but with Q deform Laplace transform, and you just have to take the limit, the various limits. Q goes to 1. And okay, so this is how we got this formula. It's the issue of contours, which, you know, as Kurt knows, not always first physicist for that, but in that case, we are sure of the result, Kurt, I will tell you, because there are many checks on this formula. So, and they all go through. So we know that the contour has to be this in that case, in the limit. Okay, so let me just say now what we can do with this formula, and if we have time, I will say how we get it, okay, and various limits of this formula. Okay, so what we can do. Okay, so the thing we're interested in is to compute, for instance, the cumulants of the current of G, of the integrated current, time integrated current. So for instance, things like expectation 1 over epsilon. So some generating function for the cumulants. So that defines some function phi of P. capital P here is some variable. And from this, you can get the cumulants, which will have of this integrated current, which will be like epsilon n minus 1 kappa n for small epsilon, and kappa n are the some numbers which function of the parameters which you want to know, and you also would want to know the distribution of the rate function for the distribution of the current phi, capital phi. Okay, so since the observable here is a bit more complicated than usual, usually you have simply a Laplace transform, so you just have a linear function here. And there's this random variable, but this random variable has a, well-defined. You can do saddle point with this random variable and a few Legendre transformation. And at the end of the day, you can find relation between all these functions. And for instance, you can compute these cumulants from the derivative of this function psi of u, this rate function psi of u, at u equals 0, which are relatively simple. You just get a bunch of exponential and you get a bunch of error functions. So from this derivative, you get these cumulants. So for arbitrary ρ1, ρ2, they are a bit bulky, but there is no difficulty of principle. So the first cumulant, which is the average current, which gives you ρ1 minus ρ in the stationary case, and put a t here. So this is for ρ1 equal ρ2 equal ρ. Let me show the second one. So it's some function of, okay, I put equal 1 for this one. G of y is some function with some error function. And so on. One of the checks I mentioned is that we can compute kappa 3, we have it for arbitrary ρ1, ρ2, and we do ρ1 equal ρ2. They have nice limits, all these cumulants. Although on this function, it's difficult to find a limit ρ1 goes to ρ2, but the cumulants themselves are perfectly smooth in u, ρ1, ρ2, everything is okay. And this we could compare with the work of very recent work of Grabsch and collaborators, which computed the third cumulant for arbitrary d of rho and sigma of rho. It's pretty heavy calculation by perturbation theory of the saddle point equation. So it's kind of a heavy calculation. It's the kind of thing you want to do. You want to do even worse than them, but okay. This is, look at their paper because this is already. You
want to discourage.
Okay, anyway, so we put ρ1 equal ρ2 and we get exactly their formula. So we are confident that it's okay. Now, if ρ1 different from ρ2, you can. What you see is you have as I say, a bunch of error functions which are centered around this. Characteristics, right? Sorry, with some rounding.
So is there an interpretation to kappa n?
Interpretation in terms of what? In terms of the cumulants or?
I think so.
Well, you have to find it, okay? Maybe.
Equals them kappa.
Huh?
Equals them kappa.
Ah, yes. Okay, maybe it was to motivate you. Maybe, I don't know. Okay, I have no idea. No idea. Okay, so the other thing we can look at is the tail. And we find that this function phi of g actually, okay, we were a bit surprised, but it turns out that this function at large g going to plus infinity is like this, it's cubic, and it's exactly the same coefficient as for the SEP. So the coefficient doesn't depend on u. And this was in a paper of Derrida-Gerstenfeld. Okay, so the coefficient of this tail, this tail does not depend on you. Although there is some interesting crossover, which I'm now going to come to. Okay, so let me mention now the question. So let me mention now two limits. So there is the SEP limit, which is new to 0. Well, it turns out, as you can see in this formula, that nu to 0, you cannot just do it like this. There's a 1 over nu here. So it turns out that this formula here, when u goes to 0, you can expand here in nu, but you're going to get on the left-hand side, you're going to get a term like 1 over nu because of this, plus something over the 1, which is a function of u. I'm going to call it pu. Okay, so this is on the left-hand side. And on the right-hand side, you're going to get something which is, you can study this function psi, and it turns out that in that limit, it has a part which is 1 over nu, and then a part over the 0. Okay, so what happens is that there is a cancellation, and that these two terms are exactly the same. Okay, I don't know if you can see it offhand like this, so it's obvious to you. But okay, that's how it works. And so then you have immediately the cumulant generating function for this limit, and this limit turns out to be exactly, I mean, it gives the correct result for the SEP. So phi of p is psi 0 of some, well, let's say minus psi 0 of u for some, okay, there's some relation between u and p, but it's easy to figure out, and then you get back the SEP. You get back the formula of Derrida and Gershenfeld, and also of Imamura, Malik, and Sasamoto, who did it for non-zero x. So x, again, is entering here, okay? Because they were interested in the tracer position of a tracer, so they needed this rate function for arbitrary position x. Okay, so this is the limit, the SEP limit. And then there is a KPZ limit, which is also very interesting. So the KPZ limit, let me write it here in part. So when I say KPZ limit, I mean KPZ equation. So for nu going to infinity, what you do is you start again from this equation, and you write rho is 1/2. So you put yourself at the maximum of sigma, okay, plus rho tilde over 2 nu. So you rescale the density around the maximum. And then the equation for this rescaled rho tilde is exactly the stochastic Burger's equation. With a noise which is this. So there's a noise term, which, so there's an epsilon KPZ if you want, which is epsilon mu square. Again, so you have to tune, you know, if you want it to be fixed, you have to tune nu to be large, epsilon to be very small, so that the product is fixed. Okay, and what happens? Okay, so it's not surprising to get weak noise. So this is weak noise KPZ equation. So it's not surprising to get weak noise KPZ equation. If of course, if this epsilon KPZ is small. And the way you see it on the formula here is that on the left-hand side, it becomes a simple Laplace transform. So you can linearize this function, which starts linearly. I forgot to say it, but it starts linearly at small u. And what you get is an expectation value over some rescaled omega. So omega is also becoming, this random variable is also becoming rescaled, and you get, okay, and this exponential, this becomes exponential of the KPZ field, HKPZ. So this is the left-hand side. And the right-hand side, the function psi actually has a nice limit, like 1 over nu square times some function of a rescaled Laplace parameter, which turned out to be exactly KPZ function. Okay. Nu square exponential minus nu square. Okay, I'm not going to write the detail, but okay. Okay, so this parameter is going to be your epsilon KPZ, which is square root of KPZ time. So then you recover exactly the weakness theory of the KPZ equation. Okay, net limit. Just one last comment. If you take directly, it's possible to work out the limit ρ1 goes to ρ2. But then this function becomes not a function of u, but of square root of u, actually. So it's develops some non-analytic behavior, and something we already did in a KPZ, stationary KPZ equation. But okay, so this is very similar again to this noise here is very similar to the one which happens in a generating function for the KPZ equation, like Alexei has looked at in his paper. Sorry?
Could you give a quick reason as to why it develops at non-analyticity? I mean, can I not move the contour past
the function psi of u becomes a function of small phi, I don't know how to call it, or small psi, of square root, v equals square root of u. Huh?
Very small.
Very small psi. V equals square root of u.
Can I not move the contour or definition of psi past row two, you develop
to do it. You can, I mean, that's what we do essentially, but I mean, we didn't try fully this, but okay, we kind of did some more rescaling thing, but you can expand this guy and then in powers of u and you move each term, okay? So you get a complicated expression, which, but okay, we did some other method where we rescale and we do integration by part and okay.
but somehow the u becomes root u when you do that.
I'll show you, sure. I'll show you. But following our discussion of yesterday, maybe there's a better way to do it. But okay. Okay, so let me now come to, I don't know, 6, maybe to this integrability business. Yeah, I just want to mention
why can compute because there is a lead.
Okay. Jeez. Ah, yeah, I forgot something. Sorry. Yes. What?
Yeah.
Sorry. Yes.
What is the special rule of the V2 function?
No, it has also, I mean, you can just think of it as a series expansion and has some coefficients.
It seems that you can do this computation just because you choose this.
Why is it coming? It's coming from this Q deformed Laplace transform that École and Alexei have computed. I can show you at the end, but time is running short, but I can show you if you want. Okay, so one thing in the KPZ limit which is interesting is that this function, this large deviation function for the probability, this one, it has to cross over from the cubic tail to the tail for KPZ, which is 5/2 exponent, and there is a scaling function, so one can compute this and find that it takes this form when both g goes to infinity, plus infinity, and nu at the same time goes to infinity. Then there is a scaling function, phi plus of some combination, which is g over 2 nu, which interpolates between the cube. So this function interpolates between the cube and the power 5f. And GT. So it interpolates between a wasp tail and a capacity tail. Okay, so let me now come to the last part, which is about integrability of the wasp.
You do a weak figure is wasp, so there is one limit, and you do the weak noise limit.
A lot of limits. Yeah.
Yeah, only you do them any order blankly.
Yeah, it looks like they commute.
Yeah. You know why?
No.
Why is it surprise or?
I don't know. I'm okay.
Not why it's difficult,
but
that was expected that it will work.
yes, I'm hiding a lot of things because
Really?
not telling you everything. This function psi is defined, it's a function of u, right? But it's actually, you see, there's a logarithm here, log of 1. So the derivative of this is log of 1 plus this.
Mm-hmm.
So it has a branch cut somewhere. So when you reach some critical point UC, which corresponds to some critical current GC, then there is another branch. So if you want to look at the tail G going to minus infinity, you have to, which means G smaller than this critical GC, you have to look at these branches. And then the limits are much more difficult because there are several branches and you don't. Okay, but, maybe I'll come back to it after this integrability business. But okay, so there are some cases where the limits are not so obvious. Okay, so I will probably erase this now. Okay, so let me look at this integrability. So so as I said in this macroscopic fluctuation theory, you can write some saddle point equation. So you start from this equation, you do, I'm not going to go into the detail of this, but you do some dynamical field theory, which just means that you represent any average of observable by some path integral, at least this is how physicists like to do it, with some action. So there is some, you introduce a new field, which is there to enforce the fact that this equational motion is obeyed. Average over the noise, you get some action, okay? And then you take the saddle point of this action and you get the standard equation for Q, which is the density field at the saddle point, and P, which is the response field at the saddle point. So the conjugated field. Okay, so let me just write them for definiteness. So the one for Q is essentially the same as the original equation, except that the noise is replaced now by the response field. Okay. Things like Denis likes a lot, and minus dTp equal. Okay, so there's some nonlinear term, some derivatives, and it has some Hamiltonian structure, so it can be written also. It can also be written from a Hamiltonian of P and Q, which I'm not going to write, but okay. And there's a minus sign here, as usual, because this response field is going propagated backward. And there are some boundary conditions, which depend on which observable you look at and what is the initial condition. So observable usually is at the final time, and boundary condition initial time. Okay, so this equation look horrible, and we played around with it also with Aurélien Grabsch, who's trying to do it. So the first thing you notice is that you can actually, don't do all the steps, but there's some collapse transformation which makes them slightly nicer. I'm not going to write intermediate steps, but okay. So you can define some Z. There's some collapse transformation like this. And then you want to symmetrize this equation because in all the cases we know, like NLS, DNLS, these equations are very symmetric in the two fields. Well, for a simple reason in this case, because they are actually, in NLS, you're looking at psi and psi star as independent field. So the equation is, of course, very symmetric. So the case we know well are always symmetric. So we symmetrize this equation, and the way what we found is we could symmetrize them by making this change of function, which okay. And so there are now two fields, which is Z and R. Okay, and it turns out that with this change, this satisfies a very nice equation, which is perfectly symmetric, and which I'm sure that Denis will recognize immediately. And the second one. So the second one is essentially the same with Z change in R and Z exchange. Okay, so this is the system. And in one of your papers, you have this system without this term. It's a paper about spin coherent state, right? Heisenberg chain, with Adam. It's not clear to me what you do with this equation in that paper, but but okay, it's in your paper. Okay, here we have, in addition, we have this new square. Okay, and as I said, spin coherent state. So in fact, there are spins behind this, and well, first of all, it has nice properties. When u goes to 0, one recover, there is some change of function, but you can map it to the NLS, and when u goes to infinity, then it's kind of obvious. If you scale R, that you get NLS system.
So on paper with new equals 0, it comes
Yeah, new equals 0.
MFT.
Yeah, so it means that
Coherent state.
it's exactly the same. So in your paper, you have exactly the same. It's just that you don't see it, but it's in your, I think Alexandre told you, but I don't know what you can do with it, but you have
But this is the simple interpretation in terms of coherent states.
yeah. So okay, so I mean, so let me come to
What I mean,
yeah.
SU2.
Sorry.
Coherent state for SU2.
Yeah. Okay, yeah. In your paper, this is what you do. Yes. Here it would be kind of a classical spin, but okay. Yeah. So what? Yeah.
yeah, that's, I mean, that's discrete, not the Schrödinger equation.
No. This is continuous. This one.
So what is the NS?
Derivative.
Derivative.
Derivative, I mean.
So derivative. So the non-linear term is dx.
Same symbol, okay. Yeah. I know,
This is a no.
Yeah,
Okay. And then of course psi again. Psi is like Z, and psi star is like R. Okay. It's a real version of a. Okay, so now what you do is you write a spin representation. So what happens is that you can consider spin on the sphere. So with its constraint, okay, and you can write the stereographic projection of the sphere on a complex plane. And so you can write it in terms of the matrix of spin, which is like this. So this matrix in stereographic representation becomes this. I'm reaching the limit. Okay, so this is just a stereographic representation. If you think of R as omega and Z as omega star, where omega is in a complex plane and S is the stereographic projection from S to omega. Okay, so this is just a parametrization. And the point is the following. The point is that you can show that one equation, this system is equivalent to the Mendeleev-Schitz anisotropic equation. Okay. And you have to also do to on IT. Yeah, it's the same here actually. You have to do also this. You always have to do this continuation. Okay, so this is the point. This is what we found, and then once you know that, so okay, so we use some old paper of Nakamura and Lakshanan, and to see where these equations were written, and once you know that, then it turns out that the system is integrable, and the Lax pair has been known for some time. So we can just use this Lax pair. We have to add a magnetic field, so there's an additional term, but apart from that, it's essentially what was in the paper of Nakamura and Sasada. 82. Oh, it's quite old. So again, we have this auxiliary linear system. Where V is a function of X3 and some spectral parameter K. And the compatibility condition of this is we can check using Mathematica, because the question is a bit heavy, that this is equivalent to the equation 1, this system.
L is the rational
Huh?
function. L is a rational function.
Okay, so L is a matrix, 2 by 2 matrix. So we're just going to show L because the other one is a bit more complicated, but L is relatively simple. It has this form. Okay. So this is a Lax matrix, and then there is this M, which is more complicated. And they also have some expression in terms of the spin. This is how they are given in these papers, in terms of the spin matrix. Okay, so I think my time is almost over. So what we did not do, okay, so we found this, but we did not do at this stage yet is to use this to do inverse scattering. Usually what happens to do inverse scattering, you solve this equation using the boundary condition at time 0 and 1. You deduce from it scattering coefficients, so the coefficient of the plane waves at infinity. And usually these equations are sufficient to give you this coefficient B and B tilde, which is half of the coefficient. And then you have to use some other condition of there's some relation with the other coefficient, which is this. And this you have to use to obtain the A of K by some kind of Riemann-Hilbert problem, which I'm not expert in, but we managed to do in some cases. And you get a solution typically in the form of some integral with precisely some log 1 minus B tilde of K, integral of K. And from this, you can extract all the conserved quantities, and it turns out that these rate functions are conserved quantities of these equations. In general. I mean, well, maybe not in general, but in the case that we looked at. So it means that you're going to get formula like this for conserved quantity, and so this is not very different from this. If you take the derivative of this, you get essentially a formula like this. So that's the other method to do to get this type of formula.
These are local conserved quantities.
Sorry?
So local or non-local?
Local. The simplest possible one usually is just the density, or for non-linear Schrodinger is just side star. But it's not the general, property. I mean, it happens that it's like this. Yes, sorry.
How the boundary conditions of that initial set of equations can transform to be, because for inverse scattering, you need a sufficiently fast decay of the initial condition.
Yeah, so there are only a few cases which you can actually do this program up to the end and have explicit forms. The question of how it decays at infinity is important. So for instance, for the droplet initial condition in KPZ, it's okay because it decays at infinity. For the flat initial condition, it doesn't, but you can still manage to get a solution. But yes, this is the type of question which are important. Okay, I think I can stop here unless you want me to tell you more about Hamel formula. Okay, it's a bit of a long, I have a full page of.
Painful formula, no one wants to see it.
It's so much, I mean, I need to do that.
Oh, well, thank you.
Okay. Yeah.
You have this classical integrable system,
Yes.
which has a saddle point of view. But the function C of U is the value of the action at.
Yes, so it's a conserved quantity for some particular initial condition.
Why it's a conserved quantity? Because it's the value of the action. Usually it satisfies Hamilton, Jacobi, or whatever, something like that.
No.
It's a conserved quantity.
Okay, I cannot. I mean, there's no.
Because am I
There's no
correct
general
saying that
relation between
C
conserved quantity and.
psi of U is the action S, the MSR1, evaluated at your solution?
Yeah, evaluated at the saddle point. Yeah. Plus the source. I mean, plus the boundary condition.
Yeah, a global action.
Yeah. So you could write Hamilton-Jacobi equation.
Yeah.
Yes, you can. I think.
This is not the way you did it. You
Salut,
first
did a
find
lot
the
of
solutions
stuff.
and you plug into the action and you compute them.
No, we didn't do it like this.
But then why is it?
Because it's
that-
complicated to actually plug it back in the action and do the calculation.
Yeah, so how you
It's so
compute?
obvious.
So how did you?
There are some cases where you can do it explicitly. For nonlinear Schrodinger, we could check that they are the same result.
So what's the solution here? How did you compute psi?
How did we compute this function? Okay, so in the case of the, I will do it in a simpler case here because here actually we haven't done it, so I cannot tell you. No, we have not used this inverse scattering for this problem. We just found that it was integrable, but it still has to be done. But okay, we know a solution by another, at least for this observable, by another method. But okay, so this turns out to be equal to the first conserved quantity, which I think there's some Legendre transform involved in this, but eventually the value of the psi square, if you want, or it's actually PQ.
You separate the variables and you have.
Anyway, we can I mean, we don't have much. You're leaving at what time? In half an hour, so we have half an hour to discuss this.
Okay.
Yeah, well, if you have any idea, we'd be very interested to know.
I wonder if you usually can compute S if you go to the you separate the variable. Hamilton Jacobi.
Okay. Yeah. Okay. We didn't do it like this, but if you have a suggestion.